Welcome to Designing Production-Ready RAG Architectures for Low-Latency Search. This beginner-focused course is for ML engineers and AI researchers. Retrieval-Augmented Generation, or RAG, is now a critical pattern in applied AI. We will cover everything from the basic concepts to deployment, focusing on how to build reliable, fast retrieval systems. Keep in mind that for major AI companies, the retrieval layer, not the large language model, is often the performance bottleneck. RAG was created to solve three fundamental problems with pure large language models. First, LLMs have a knowledge cutoff since their training data is static. Second, this leads to hallucination risks when they lack current information. Third, the context window limit means you can't feed an entire knowledge base to the model. RAG solves this by retrieving only the relevant current documents at query time, grounding every answer in facts. A RAG system consists of two distinct pipelines. The indexing pipeline is an offline, batch job that chunks raw documents, embeds them, and stores the vectors. The query pipeline runs in real time on every user request and must be fast. It involves embedding the query, retrieving a large set of candidates, and often running an optional re-rank step to select the best documents before generating the final answer. All latency optimizations target this query pipeline. The retrieval layer has three main components. The vector database, like Pinecone or Qdrant, stores dense embeddings and uses approximate nearest neighbor search. The embedding model converts text to vectors. Crucially, you must use the same model for both indexing and querying. The retriever and re-ranker uses cosine similarity for initial retrieval and a cross-encoder model for precise re-ranking. The target latency budget for the entire query pipeline is often less than 500 milliseconds. Here is production Python code for a query pipeline using LangChain and Qdrant. Notice the use of asynchronous functions, common in production web servers. Key configurations include using max marginal relevance, or MMR, for diversity in retrieval, and setting "fetch_k" significantly higher than top_k. Finally, always return source documents to allow users to fact-check and build trust in the system. Moving from a prototype to a reliable system requires mastering four key patterns. Start with chunking strategy. Fixed size is the baseline, but consider semantic or hierarchical methods for better quality. Implement caching. Semantic caching can deliver 30 to 60% cache hit rates, drastically reducing latency. Adopt hybrid retrieval, combining vector and sparse search like BM25 for robustness. Finally, prioritize observability by tracking P95 and P99 latency, not just the average. RAG development is about trade-offs. Should your chunk size be small for precision or large for context? Should your top K be small for speed or large with a re-ranker for better recall? When deciding on vector DB hosting, managed services offer zero ops overhead, while self-hosted options are 5 to 10 times cheaper at scale. Remember to tune only one variable at a time using an offline evaluation set before making production changes. Notion's production case study provides clear lessons. They found that domain-aware block-level chunking improved retrieval precision by 18% over arbitrary fixed-size chunking. Implementing semantic caching cut their P95 latency from 2.1 seconds to 380 milliseconds. Most notably, adding cohere re-rank without changing their embedding model or vector database improved user-rated answer quality by 22%. The frontier of RAG is adaptive retrieval and query routing. The key insight is that not all queries are the same. A factual query needs direct search, while a comparative query requires multi-step retrieval and synthesis. An ambiguous query might need a clarification step before targeted search. Advanced tools like LangGraph and Self-RAG enable systems to choose the best strategy dynamically. Here are the key takeaways. First, design a two-pipeline RAG system with distinct performance requirements. Second, choose appropriate models and databases based on scale and budget, understanding the trade-offs. Third, apply advanced techniques like MMR and re-ranking for quality. Fourth, use caching and hybrid retrieval to meet strict low-latency targets. Finally, recognize when to evolve toward the robustness of adaptive retrieval. To continue your learning, here are some curated resources. Start with the practical guides from LangChain and Llama Index. Use RAGAS for robust evaluation before tuning. Explore foundational papers like Self-RAG and Flare for adaptive strategies. Finally, investigate tools like Cohere re-rank and dive into the documentation for vector databases to understand their internals. The Retriever is the heart of every great RAG system. Build it with precision, measure its performance obsessively, and iterate relentlessly. Thank you for viewing this video. You can find the full course and more resources on RAG architectures at the link on your screen.